In grade 1, you learned to add numbers together. 3 plus 4 in grade 1 was always equal to what? 7. In fact, 4 plus 3 was also equal to 7. Right? It didn't matter what order you added them in. 3 plus 4, 4 plus 3 was always equal to 7. In grade 1, whether you realized it or not, you learned to add scalars together. Now, in grade 6 or so, you learned to add 3 plus negative 4. And you also learned to add negative 3 plus 4. This one would be negative 1, and this one would be positive 1. So in this case, we're saying that 3 plus 4 doesn't necessarily equal 7. 3 plus 4 can equal 1, depending upon what the sign of the 3 is and what the sign of the 4 is. For us, the sign represents a direction. So really what you learn to do in grade 6 is add vectors, but adding vectors in one dimension. Maybe you had 3 to the north and 4 to the south, or 3 to the south and 4 to the north. We learned to add those together. It's pretty simple, okay, but in the end, it was still a different way of adding. Yesterday, we introduced another new way of adding vectors together, but vectors that aren't on the same plane, not both north and south or east and west, but rather if we have two vectors together on different planes. So maybe we got a 3 to the north and a 4 to the east. How do we add those ones together? Well, remember, ultimately, we're still adding them together. We're still adding vectors together. It's just that now 3 plus 4 doesn't necessarily equal 7, and 3 plus 4 doesn't even necessarily equal 1. So how do we do it? How do we add them together now according to this new two-dimensional thing? Well, the goal, there's always a goal here in this method, and that's going to lead us to solving for the sum of these vectors. The goal is always to get a right-angled triangle vector diagram. Now, you don't even really know what a vector diagram is yet. You'll see in just a moment here. But you know what a triangle is, right? From our vectors, our 3 and our 4, we need to get a triangle. It's in the form of a vector diagram. And then we need to use a little bit of trigonometry, including sine, cos, tan, and including the Pythagorean theorem. So let's learn to draw these vector diagrams that we turn into these right-angled triangles and then use some trigonometry on. Here's the rules. There's 3 of them. The first rule is, well, we got to be able to draw a vector first. A vector is a line segment that has an arrow on the end of it that shows the direction. So if I have a 3 to the east, it might look like this. If I have a 4 to the east, it might look like this, a little bit longer than 3. We always try to draw it roughly to a scale, although we're not using our ruler to measure it, so it doesn't have to be perfect. Bottom line is the 4 should be a little bit longer than 3. If I have a 4 to the south, it would look like this. If I have a 10 to the west, it might look like this. A vector is a line segment with an arrow on the end of it that shows direction. Notice this 10 to the west, I don't have a negative in front of it. Why not? Well, the negative is meant to show direction. I already have direction shown here, right? How, Isaiah? With the arrow. So I don't need the negative on there when I'm drawing it as a vector graphically, because the arrow shows that direction already. So you got to draw each of them as a line segment with an arrow showing direction. In other words, you got to draw each of the vectors. But now, how do we connect them together? These vectors, if we're adding them together, should be drawn front to back. What do I mean by that? Well, if this is a vector, then this would be the front of a vector, and this would be the back of a vector. So when I'm drawing 2 vectors to add them together, I need to draw them such that the front of one vector connects with the back of another vector. If I'm adding 3 plus 4, but the 3 is to the east and the 4 is to the north, then it might look like this. 3 to the east, and 4 to the north. Notice it's drawn front to back. Now, I do have another option here. It's not the only way to draw this, because in the end, we know 3 plus 4 is the same as 4 plus 3. So I could choose to draw it like this if I wish, and I still end up getting the same thing. 4 plus 3 is still equal to the same thing. Notice this one's also drawn front to back. Now, the resultant vector, which is really what we're looking for, the sum of the vectors, the resultant vector is always drawn from back to front, or we can say from start to finish. So the resultant vector would be drawn from back to front, or start to finish in this one, back to front, or start to finish in this one. What do you notice about those two red resultant vectors? They look pretty much the same, don't they? They should, because 3 plus 4 is the same as 4 plus 3. It's not a coincidence that they look the same. Doesn't matter how you draw it. Okay, they're both correct. You end up getting the same resultant vector either way you look at it. Just like if one person adds 3 plus 4 and the other person adds 4 plus 3, we end up getting the same thing. Let's have a look at a couple examples here. The first two, I think you're going to find are really, really straightforward. We're adding vectors together, but in the first two, we don't even need to draw a vector diagram. How come? A and B, no vector diagram necessary. You could if you wanted to, but it wouldn't really be that helpful to you. How come? Why is it not necessary to draw the vector diagram there? Yep. Yeah, we're on the same axis in both cases, right? The same plane in both cases. The first one is north and north. The second one is north and south. If we define, for the first two questions, if we define north as positive, then in the first question, all I got to do is say 10 plus 20 is equal to 30. 30 meters to the north. And in the second one, it's a little bit harder, but not much. We've done this a million times before. We'd say 10 plus negative 20, because it's to the south, ends up giving you negative 10 meters. So negative 10 meters or 10 meters to the south. Nothing new there, right? We don't need to draw the vector diagram because it's not in 2 dimensions. But as soon as we introduce the third question, where we have 10 meters to the north and 20 meters to the east, all of a sudden, it becomes one of these newfangled questions where up until today, we didn't know how to add those together. All right. Let's erase this so we have some more space to work here. 10 meters to the north and 20 meters to the east. Let's draw the two vectors first of all. This is about 10 meters to the north. This is about 20 meters to the east. Drawn about twice as long as the first one. Now those are two vectors, but we haven't added those together then yet. They're just two random vectors. If we want to add them together, we got to make sure we draw them front to back. Now we've got a couple of options to do that. We could say 10 meters to the north and then front to back 20 meters to the east. Or we could say 20 meters to the east, and then front to back, 10 meters to the north. In the end, in both cases, we get the same resultant vector, always drawn from back to front or from start to finish. Draw whichever way you want, both ways work. Now, we got to find the value of R, we're going to call it. R being the resultant vector, the sum of these vectors. So how do we find the value of R? Next. The Pythagorean theorem. Now, I'm going to erase this one because in the end, we know we're going to get the same value for R as we get for R over there, right? So I'll just create a little bit of space. I'm going to erase one of them. The Pythagorean theorem says a squared plus b squared is equal to c squared. What's c here? Which line is c? Yeah, it's R. It's the longest one. The hypotenuse is always going to be the longest one. So instead of saying, for us in physics, a squared plus b squared is equal to c squared, we're going to say a squared plus b squared is equal to r squared. Same thing, right? Therefore, r will be equal to the square root of a squared plus b squared. Now, does it matter which one's a and which one's b? Well, as long as you use the 10 and the 20, it doesn't matter. We're going to say r is equal to the square root of 10 squared plus 20 squared, which is the square root of 500, which I believe is 22 meters. Is that right? 22.36, which we're going to round to 2 digits and get 22 meters. Now, is that good enough? No, it's not. What have we just solved for? What is R? What's it called? The resultant vector. It's the sum of the other vectors. The sum of other vectors, the resultant vector, is a vector in itself. And a vector requires direction. So we have to indicate direction here somehow. Let's do that by calculating an angle. Theta is our angle. And our angle theta is always measured at the beginning of the vector diagram. So some people will get this and say, oh, well, how do I know not to draw it right here? Well, you know not to do it right here because that's 90 degrees. You know not to do it right here because that's at the end of the vector diagram where it becomes front to front. You always draw it at the start of the vector diagram. Now we're going to use a trig function to solve for theta. And if you remember, there are three basic trig functions and three that you've got to be aware of in physics 20. There's sine is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, and tan is equal to opposite over adjacent. Tell me, what's the hypotenuse here? Which one is the hypotenuse? The 10, the 20, or the 22? 22. What's the adjacent side? Not the 20. The adjacent is the 10. The adjacent is the 10. The adjacent one is the one that touches the angle, but not the hypotenuse. So my adjacent is the 10. The opposite is the one, the only one, that doesn't touch the angle. So that's going to be the 20. We're going to use the tan function here since we have opposite and adjacent. Tan theta is equal to opposite over adjacent, or tan theta is equal to 20 over 10. If I want to rearrange this to solve for theta, a little bit different here. I'm going to say theta is equal to the second function, or inverse tan, of 20 over 10. Now we're going to go through this on our calculator to make sure that you can do this. On our calculator, the first thing that I want you to recognize is whether or not you're in degree mode. You need to be in degree mode. There's a quick little check for that. Everybody on your calculator right now hit sine 90. Sine 90. If it equals 1, you're good to go. If sine 90 equals 0.89, you're not good to go. It means you're in radian mode. Does anybody have a calculator right now that's giving me 0.89 for sine 90? Yep. All right, so we got to change that then. Here's how we change that on your T83s or 84s or 85s. Go second function. Sorry, no, don't go second function. Go mode, and then scroll down to the third option. You can see that for me, it says degree is highlighted. If for you it says radian highlighted, then you need to go over here to degree, press enter, clear it, and then hit sine 90 again as your little check. Now it should equal 1. When you're in degree mode, here's how we're going to calculate theta. We're going to say second function, tan. That's the yellow button, tan, or for some of you, it's the blue button, tan. Equals 20 divided by 10, end the bracket there, and it ends up being 63 degrees. Now, we're going to leave it there today, but understand that that's still not enough. Okay, it's kind of like saying, Mr. Dickie, what's your position? 3 meters. What do you mean? 3 meters north of the front wall of the whiteboard. 7 meters south of the back wall. Right? We need a frame of reference, right? 63 degrees what? Well, we have to express that, but we're not going to worry about that today. We'll worry about that on Monday. What I'd like you to do for homework over the weekend, please, is take a look at your next worksheet. That's the one that's titled Physics 20 2D Vector Worksheet. It's after your velocity time graph worksheet in your booklet. And I'd like you to simply do the first 3 questions on that page. They're all just like this. Okay. We have most of the vector diagram drawn in those cases. You'll need to draw the resultant vector. You'll need to calculate the value of the resultant vector, and you'll need to calculate that angle drawn from the start of the vector diagram.